Hello everyone. Today we are going to cover one of the most fundamental derivations in quantum mechanics. That is how we get the time independent Schrodinger's equation from its parent, that is time dependent Schrodinger's equation. So this is a crucial step. The time dependent Schrodinger's equation is the full and fundamental laws of quantum motion, but it's often very difficult to solve. The time independent version of the one we used to find the specific energy levels and wave function of the systems like atom, which form the basis of chemistry and most quantum physics. So we will begin with the full Schrodinger's equation, that is the time dependent one. It describes how a quantum state, the wave function psi, evolves in time. So the time dependent Schrodinger equation is given by iota h cut del by del t of psi of x comma t equal to h cap psi of x comma t. So here I is the imaginary number iota and h cut is the reduced Planck constant, that is h by 2 pi, and psi is a wave function which depends on two independent variables, that is x and t, and h is the Hamiltonian operator. So now the Hamiltonian is the sum of the kinetic and the potential energy operator. So we can write for our own understanding that h bar equal to t bar or t cap, let us say, plus v cap. So it means that minus h cut square whole upon 2m del square or del 2 del x2 plus v of x comma t. So this is the full equation of our starting point, and it is like the Newton's F equal to ma for quantum mechanics. So the key assumption, a static potential, that time dependent Schrodinger equation is a complex and partial differential equation. To simplify it, we can make one critical assumption, that is, we assume the scenario of the problem like the potential energy V does not change in time. So the V, which is depending now on x and t, becomes just V of x. So assumptions that V of x comma t is independent of time. Therefore, V of x comma t becomes V of x. This is a very common scenario because like the electric potential holding an electron in a hydrogen atom, it's just Vr, and the wall of a particle in a box, they don't move, the wall doesn't move, so it does not change with time, the potential. Therefore we can consider that Vx, and also the potential for a simple harmonic oscillator, that is Vx equal to half kx square. With this so with these assumptions, our Hamiltonian operator h now only has derivative with respect to x and function of x. It has no time dependency at all. So now the method we are going to apply, that is separation of variable. So in our last lecture, in the particle in a 3D box, we have used this method, separation of variable. So now we apply the powerful that is mathematical technique, which is separation of variable, and we guess that the solution psi of x and t can be written as the product of two separate functions. One that only depends on position, and also with multiplied by another one which only depends on time. So our psi becomes psi of x comma t becomes, let us take one more function as psi naught, let us say, which is depending only on x, and phi which is only depending on t. So this small or psi naught x is the spatial part, and phi of t is the temporal part. Now if we substitute this back in our time dependent Schrodinger equation, then we get iota h cut, just a second, yes, iota h cut del by del t. So this will be psi naught of x and phi of t equal to Hamiltonian operator into psi naught of x and phi of t. So now let's evaluate these derivatives. So the left hand side we will get, let us write LHS over here. So in left hand side we will get the time derivative del by del t ignores the psi naught x, so because it treats it as a constant, therefore we get I h cut psi naught of x into del phi of t by del t. And in the RHS we get the Hamiltonian operator which ignores now that time because it treats it as a constant, therefore we get phi of t into Hamiltonian of psi of x, psi naught of x. So our new equation that becomes I naught, or sorry, iota h cut psi naught x del psi by del t equal to, or let us take this as psi of t because it is a function of time, equal to phi of t into Hamiltonian of psi naught x. So now here comes the separation step. So now what we are going to do is the crux of this entire derivation. We are going to divide the entire equation by our original two separate function that we have assumed. So we have assumed that psi of x comma t equal to psi naught of x and phi of t. Therefore if we divide it with, therefore we get I h cut into now we get here del phi of t whole upon psi naught x, and here psi naught x gets cancelled, and then it becomes here phi of t to del t. Or let us write here dt. So it will be dt. If you write dt over here, then it become Hamiltonian or 1 by psi naught of x into Hamiltonian of psi naught. So now you can see that this part, the LHS one, only depends on time. let us write it on time. And this right side part RHS, it only depends on position x. On x. So the core argument, that is separation constant. Now if you think about this equation, the left side is only a function of time and the right side is only a function of position. So how can a function of time be equal to function of x for all possible values of t and x? So if I change time, the left side might change, but the right side cannot change because it does not depend on time. And if I change x, the right side might change, but the left side cannot change because it does not depend on x. The only possible way this equation can be true is if both sides are equal to be the same constant. And let us consider this constant as E. So it becomes, we'll just copy it over here. And also we'll copy this one. So this is also E and this is also E, and E is a constant. So why did I call it E? If you look at the right hand equation, the Hamiltonian operator is an energy operator, and the equation Hamiltonian of h psi naught by psi naught has a unit of energy. So we rightly identified this separation constant E as the total energy of the system. So now solving the two new equations, that is we just you can see that we just turned one hard partial differential equation into two much easier ordinary differential equation. That is the equation 1. Let us consider this equation as equation 1, which is the temporal one. The temporal, that is time equation. So which one is it? So it is iota h cut whole upon phi of t into d phi of t whole upon dt, which is equal to E. So now we will just solve for phi of t. So how can we do it? We can rearrange this one as d phi of t whole upon phi of t, or let us just write over here phi, equal to E by E by h I into h cut, and then here we get dt. So now we know that 1 by I equal to 1 by I into I by I, which is equal to minus iota. So we will use this thing over here. So del phi by phi equal to minus iota E by h cut and then dt. So what we get as phi of t, just let us write this as phi of t. So phi of t becomes, if we integrate both sides, then it becomes phi of t equal to e to the power of minus iota E by h cut and here it becomes t. So this is the temporal part. So this is our time evolution factor. It's a complex exponential and a pure phase. So what does it tell us? It tells us that the wave function oscillates in a complex plane. You can see here iota is there. Therefore it oscillates on a complex plane with angular frequency, that is omega equal to E by h cut. And this is the equation 1 and equation 2. That is our spatial part. Spatial position equation. So the spatial one is, we have got 1 by psi naught of x into Hamiltonian of psi naught x equal to energy. So let's solve for this one. We just multiply both sides by psi naught x. So it becomes h Hamiltonian, then psi naught x equal to E into psi naught x. And this is the one which is time independent Schrodinger equation. So it is written in the Hamiltonian form. So we can, as we know that Hamiltonian operator we have seen here in the first, that it is this part. So we can write it as the expanded form also. So what will be the expanded form? It will be, the first we'll write the Hamiltonian, that is del. We'll just copy it from here. Copy and then we'll paste it here. So this is the Hamiltonian, and then we get psi of, and this Hamiltonian will become only here the function of x and not the function of t, because we have assumed that it is only depending on x. So this is psi naught of x equal to energy times psi naught of x. So what it becomes, minus h cut square by 2m del square by del x square psi naught of x, the wave function, plus v of x psi naught x equal to e times psi naught of x. So we'll put it inside a box. So this is the same equation that we used in our past two lectures to solve the 1D box and 3D box problem. And now the stationary state, or the solution, the time independent Schrodinger equation, this is an eigenvalue equation. So it says when the Hamiltonian operator h cap acts on the wave function psi of x, the result is just the same wave function multiplied by a constant e. That is, we can say it from here, when the Hamiltonian operator is operated on the wave function, then we give the same wave function multiplied by a e. And the psi naught of x is the energy eigenstate, and the e is the energy eigenvalue. So solving this equation for a given v of x gives us set of allowed energies, that is E1, E2, E3 and so on, and their corresponding wave functions, that is psi naught 1, psi naught 2 and psi naught 3 and so on. These are the energy level of the system. So what is the full solution for a state with a specific energy En? We just put our two pieces back together, that is the psi of x comma t equal to psi naught of x and phi of t. So if we do it, then what we will get? Psi of x comma t equal to, let us suppose this n for any nth one, and the phi of t becomes e to the power of minus iota e by h cut and then t. So these are called stationary state. Why? Because let us look at the probability density, that is psi square. So if we do it psi square, so what we will get? So let us take this as n because we are considering it for the nth one. Therefore psi n of x comma t, and we'll take modulus of this and then square it, equal to, we'll get a conjugate, that is psi of n and then star over here and psi of n. So it is becoming psi naught n of x e to the power of plus iota e by h cut and then t. So this is the conjugate part, and the original part will be psi naught n of x e to the power of minus iota e by h cut and then multiplied by t. So what it becomes? So this is equal to psi naught n and the conjugate one. So just a second. So here just we missed the conjugate sign. So this is the star, and then we get this is a function of x and multiplied by the same, the original one, and which is also a function of x, and then we get e power 0 because this and this multiply, and if we add that, it will become 0. So this one we get it as psi square. So now it is psi naught n x and then whole square, which is equal to this part. So now we can see that the probability of finding the particle at position x is independent of time. Though we started with time, but it is independent of time as it is coming here. So even though the wave function itself is oscillating in the complex plane, that is with its e power minus iota e by h cut and multiplied by t factor, the physical and the measurable probability distribution is completely static. So this is what an energy level is, and it is a stable standing wave probability. So what we did, first of all, we did in this lecture, we assume that the potential is independent of time, and we used the method of separation of variable, and we did the LHS and RHS part after separating the variable, and then we found out that this is independent of time. This is independent of x and this is independent of time. So we need a constant for that to be true for all x and t. Therefore we got energy as a constant. So this is the temporal equation, that is, after solving we got this part, and this is the spatial equation, that is with the Hamiltonian operator, and we got this as time independent Schrodinger equation. So this is the one. So first of all we derived this one, and after we found out that the probability density or probability of finding the particle is independent of time. Though we started it with the factor of t, the equation with the factor of t, but we reached with the factor of only x. Therefore, the probability of finding the particle is only depending on x and independent of time. So now we will just write over here that what are the key things that we need to remember. So key points. So the key points are, I'll just write one by one. The first one, that the time dependent Schrodinger equation is the general law that is iota h cut del psi by del t equal to Hamiltonian of psi. So this is always true. Always true. And this governs all quantum dynamics. So this is the time dependent Schrodinger equation is the general law, and that is, this equation is always true and governs all quantum dynamics. So the second thing in this lecture that we need to remember is our key assumptions. Assumption. That is, V potential is independent of time. Hence, it becomes V of x comma t to only V of x. And we also need to remember the method that we used, that is separation of variable. That is psi of x comma t equal to psi naught of x and multiplied with phi of t, where x and t are the independent variable and psi is depending on x and t. So psi is a function depending on x and t, and x and t are the independent variable, and here psi naught is a function that is only depending on x, and phi is a function that is only depending on t. And the fourth thing that we need to remember is the result, that is the time independent Schrodinger equation. So in the Hamiltonian form we will write, just to save our time, E into psi naught x. So here we can use psi naught, anything, because this is just the wave function, and this is a eigenvalue function, very important one, eigenvalue function or eigenvalue equation, let us say function, that solves for the allowed energy level E and the spatial wave function psi naught of x of this system, particular system. And the V, or the fifth one, that is the stationary state. The stationary state. That is the phi of, here what we got, I just copy it from here. So this is the stationary state. So we'll just write it over here as a topic, stationary state. So in stationary state, what we got is that the probability of finding the particle is independent of time. So this is what we learned in this lecture. So I hope you understood, and thank you for watching.